each point is a distance. Okay, what can we say? Okay, so what can we say about this inner product h comma semicolon x? For now I'll emphasize that it depends on the point x. Well, maybe I should say xy or something, or z, to otherwise it will look at this thing. Well, what do we know? What can we say about this? Well, if we know nothing, we can't say anything. What we know is that this is preserved by symmetries of H. Okay, so the first fact here is proposition is the corresponding angles are the Euclidean angles. Okay, so the angles coming from hyperbolic metric are the same as the Euclidean angles. Recall that any inner product gives you angles. Why do we know this? So reason, there are symmetries fixing any point and inducing rotations, and here by rotations I mean Euclidean. Okay, I'm not going into details of this, but this is easier to see in the disk model. If we take our point to be the origin, well then obviously what happens is, if I look at z goes to alpha z with mod alpha is 1, this is a biholomorphic map and it's simply a rotation. Okay, and so in particular, given any vectors here, they are simply rotated at the origin. Okay, their length is not changed, they are simply rotated, and so the induced map on the tangent space is just a Euclidean rotation, and this has to be a symmetry. Okay, from this one can conclude that rotations at any given point are symmetries, Euclidean rotation of the given inner product, and this can only happen if the angles are the same. Okay, so that's the relatively easy to see proposition. Now at any given other point to say the same thing is not so easy, but it uses the fact. Okay, so in general you use holomorphic maps preserve angles. This is a basic property of complex analysis. So putting these together, okay, with a leap of faith, what we can see is that the new metric differs from the Euclidean one by not very much, namely the angles are the same. Okay, so let me now use the term conformal metrics. Okay, so as this inner product at whatever point z has the same angles as our usual inner product, which I'll put an E to emphasize is Euclidean, we have, well, now if two inner products give you the same angle, simple linear algebra tells you that this is some function phi of xy, okay, where z is x plus iy times the Euclidean angle. So from trying to find this complicated object which is an inner product at each point, we are reduced to finding a function. Okay, now what do we have by further symmetries? First of all, z goes to z plus a in R symmetry implies phi of xy is in fact only a function of y. Okay, so because we have horizontal translations, it tells you that if I take a pair of vectors here and look at their inner product, or I translate them and take the pair of vectors here and look at their inner products, these two inner products should be the same. Okay, but in one case is the Euclidean inner product multiplied by phi at this point, and in the other case phi at this other point, and since they're equal, so the scaling factor should be independent of x. It's only a function of y. And then secondly, z goes to kz being a symmetry, okay, implies that c of y is some constant by y squared. Okay, let me justify this, because this is let's take any point and let's look at a vector here. Okay, now kz, will take it to another point above and a much bigger vector, much bigger in the Euclidean sense, if k is large, of course. Namely, this has length, so if this has length 1, this has length k, Euclidean length k, but the hyperbolic length should be equal. Okay, that can only happen if we scale, okay, that is, if we scale the hyperbolic norm by a factor of y, 1 over y, sorry, over the Euclidean norm, to cancel the fact that things have expanded. Okay, so the y squared comes for the inner product. By the way, I put a 1 over y, in fact. So in general, I would have root c here, but I can, without loss of generality, I could take it to be 1. Well, it's a loss of generality, but nothing else. Okay, so that is to say, we have a metric which is 1 over y times this will, the scaling invariant forces this. Okay, so this is really the only, so this is forced, so thus we have a formula. Hyperbolic norm is 1 over y. Okay, I think this deserves a new page. So thus hyperbolic norm is 1 over y times Euclidean norm. Okay, so this is the big formula we have deduced. Let me just recall the steps that were involved in deducing this formula. We just looked for a metric of this form. Okay, so I should say we should verify that this works. Okay, and what should we verify? For z goes to 1 over z as well, minus 1 over z as well. Okay, so this is the exercise to end this little screencast. So what we wanted to do was we wanted to find out if the symmetries of the upper half plane or the unit disk looked at as complex analytic objects correspond to something geometric. Okay, namely, are they isometries, or is there some distance which is preserved by these symmetries? Okay, well, we tried to work out what that distance was, and a scaling factor is arbitrary, because if any distance is preserved, some scale of that is arbitrary. But otherwise we just assumed this distance is of this Riemannian form, that firstly the angles are the same as the Euclidean angles, and next that the scaling factor which works is 1 over y. I mean that this is the only scaling factor that can work. Well, but in deducing this, we also ended up checking that it was preserved by right translations and also by the scaling maps. What we didn't check was this circle inversion map, that this circle inversion map preserves the result, but one can verify this by a simple calculation, and that tells you that the symmetries of the upper half plane are exactly the maps that preserve this. Okay, so with that I will